like to start our second talk of the day, which will be given by Devora Zalaznik on towards sharp cubical small cancellation condition.
Okay, hi. Hello, everyone. Thanks for having me. Hi, Alex. Happy birthday. So I also wanted to say a few words to Alex, and it's a little difficult at this point of the conference because a lot of people have already said a lot of things. So I think I'll try to describe the experience of being a student of Alex in the last few years. And it's not just me. I think my friends agree with me. So it's like you have a very busy, kind grandfather that really cares about you. And so if you want to chat or you want him to read something that you wrote, he will find the time. It can be on the way, when he's driving his car somewhere, on a flight, but he will find the time. And in this short time, you will feel like you are the most important person on the planet. And he will give you such a good feedback and great ideas, so you will feel really, really lucky. So thank you, Alex. I really love you. I really admire you. It's an honor to be a student. And now I'll talk about something else before Alex will say that it feels like a mitzvah party or something. So the plan is to compare between classical small cancellation and cubical small cancellation, and talk about the gap between the conditions, and then a few words about my research. So, about my research? Okay, so as a warm-up, let's start with classical small cancellation. So we start with a presentation, a group presentation. So we have S a set of generators and R a set of relators, and the starting space is a bouquet of circles. We have a circle for every generator. So we call it X sub S. And the starting group is just phi 1 of X S, which is the free group of S. Now, the relators will be just cyclic words. So closed gas in axis XS. Now we want to keep the relators, so we glue disk along every word that we want to be trivial. So we get algebraically we get the group Fs modulo the normal closure of R. Okay, now the point of small cancellation is to measure overlaps between relators. So we want to define a piece, which is the concept of overlapping. So what's a piece? A piece is a common subword of two relators or two different cyclic appearances of relators. So geometrically, we can imagine two circles. This is R1, this is R2, and we have a subword here that they both have. Let's call it P. Let's give a simple example. So if we have A, B, and C as generators, and we have here A, B to the 7, A, B, 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 A, C to the minus 5, then we have pieces. For example, AB is a piece because it appears here and here. Also, BA is a piece because we have it here, and also here we have B and then A. BA is not a piece because it's appeared just here. And if we take C to the minus 4, it's also a piece because A, C minus 4 is not exactly the same as C minus 4A. It appears here and here. Is it clear? Okay. The last one, so C to the minus 4 is a piece because it appears in two different ways here. You can take A C to the minus 4 and like A is not a part of the piece. Maybe I didn't explain it correctly. Like piece is C to the minus 4 and it appears differently because here you have the A on the left and here you have the A on the right. Okay, so two different appearance of C to the minus 4. Like for example, if I'll just have like for this case, if I don't have any other word, it's not a piece here because I don't have any, like it's the same if you take C4 and C4.
AB is not a piece because the first relation only needs the second.
AB is a piece because
AB is not a piece if you only have the first relation.
yeah, sure.
You need both of them.
Sure. Okay, so now let's.
Why would it be a piece if you have only the first?
You can see the difference if you rotate it the same.
Yeah.
With full symmetry of the whole relator.
Okay, now let's.
No, you have BAB and you have ABA. What would have been a piece anyway?
I don't think you're talking on, like, I think you talk on the other example. It's not the same example. Like
Let's say you had only the first condition, only AB to the 7.
only AB to
Then
7.
AB would have been a piece.
No.
Why not? You have ABA and you have BAB.
Okay, it's like you're in a circle. It doesn't matter where you're looking. You need something else so you can say that it's different. Okay, now, so this is the classical case. And now let's talk about cubical case. So,
Haven't given any conditions. So
Yeah,
just
I know.
describing what pieces
yeah,
are.
yeah. Okay, so in the cubical case, we're going to have, again, a presentation, but it's going to be a cubical presentation instead of the representation that we have here. So we'll take X, which is a non-positively curved cube complex, and the relators will be Yi to Ym. Those are local isometries. All of them are local isometries from Yi into X, and each Yi is itself a non-positively curved cube complex. So here's the starting group is pi1 of X, and it already has an action on the non-positively curved cube complex. Yeah. So now what we want to do, again, we want to kill the relators, but they're not just a word, so we need something else. So what do? We take cones and we glue them on each relator, and this is how we get the group, which is pi1 of X modulo pi1 of the normal closure of pi 1 of yi, and we call this space that I just described the presentation complex. So presentation complex.
Just checking, it's assumed that everybody knows what a non-cubical, non-positively curved cubical complex is. That's not going to be explained, right?
Yeah.
Okay.
Okay, so the presentation complex will be you take x and attach cone on every yi. Okay, now pieces. So the relators yi,
These maps, they have to be injective also, or not necessarily? The YIs, can they be inversions, non-injective?
it's local isometry, so you just need like no folding, no
But
vanishing.
globally can be non-injective?
Yeah. Okay, so the relators yi to x lifts to the universal cover of x, and those elevations will be the analog to occurrences of the relators in the classical case. So now if you want to define pieces, it's going to be a bit more complicated because we have the relators like in the classical case. So this gives us cone pieces. And we can try to imagine that if yi is just a circle, so if you look at yi tilde and yj tilde and they are different, then the cone piece is something like this again. But the problem is that we also have squares that come from the non-positivity curved cube complex X. So we need to define another kind of piece, which is a wall piece. I'm not going to define it like exactly because it will take a lot of time, but I can draw a picture. So if we have a relator, and a row of squares, then this part that they share is a wall piece. Okay. So
The intersection is on the wall or on the one skeleton?
it's on the one. It's like on the boundary.
So the wall pieces come only from one relator with the complex X and not from two relators?
Exactly. Okay, so we have pieces, and we want to find a way to measure them. And the way is to define a tool, which is called disk diagram. And what's a disk diagram? So we have a combinatorial map from D to X. And D is a compact, contractible combinatorial to complex with the chosen planar embedding. Okay, Now the boundary of D is maps to a loop in X. Now you can forget about all these words. You can just think about D as a combinatorial fitting of the word. You have a word, you have a circle, and then you just fill it. So it's a planar object. It's very easy to look at it and to try to analyze pieces. I'll just say that if we're looking on the, like in the classical case, these diagrams are just like X will be the representation complex. And D have only relators, only relator sets. And it's actually, it's a Van Kampen diagram, if you know what it is. And in the cubical case, it's a bit more complicated because we have X star, which is a cone of space. Remember, we take the non-positively curved cube complex, and then we glue conus on each relator. So we have a cone of space, and D will have two kinds of cells, cone cells, which are the relator cells, and also squares coming from X. So now we are ready to define the condition of small cancellation. So we have a lot of conditions. I'll just talk about one of them and mention another one. There's more. So the condition is called CP non-metric small cancellation condition. And the condition is very simple. In the classical case, the meaning is that no relator is a concatenation of fewer than P pieces. Okay, so for example, C6 is just to say that at least 6 pieces needed to go all the way around. So if this is a relator, you need at least 6.
This is a condition that guarantees what?
This is a condition that guarantees a lot of things. I'll talk about Greendlinger theorem, which is a very strong control on disk diagrams, and it yields to very good stuff, like I'll say in a minute, but word problem. Yeah, okay. So this is C6 in the classical case. Now, in the cubical case, here it is. Okay. So I'll just. Yeah. Okay, in the cubical case, it will be very similar. CP will be no essential closed path in any yi. Okay,
There's the P.
sorry,
Where's the P?
is a concatenation.
Of
The
what
same,
set?
sorry, yeah. Okay, the same condition, just about, not about a word, about all the loops in yi. So, okay, now there's another condition. Okay, the problem with this condition is that it is like, it's a counting condition. So if for example, I have some very short, tiny 5 pieces, and then I have one long, it could be sometimes problematic. So we have another condition, which is called the C prime lambda condition, which is a metric condition. Both are interesting for different goals, but I'll just say that historically, for the classical case, if you have C prime 1/6, then you can get something called Greendlinger theorem, which you can use to get then algorithm, and you can use it to solve the word problem. So the idea is like this: if you have the Greendlinger theorem saying something like this: if you have a disk diagram, then it will have a cell lying on the very close to the boundary, so that at least half of the pieces will be on the boundary. So you can, so if you have a closed path for a trivial word, you can, you don't know if it's trivial, but you can replace the long way through the boundary with the inner part of the cell, which have probably less pieces, so you can short the word, and then you can do it again and again, and decide if the word is trivial or not. So this is the idea, but now I want to talk about C6, not C prime 1/6. So C6 also gives us Greendlinger-type theorem, which is not about shorten the word, but again about like peeling a disk diagram again and again and get very strong conditions on the diagram. So this is the case for the classical small cancellation. And now the question is, what happened in the cubical case? So I think just by the way, I didn't wrote it, but this is work done in 1912 plus Greendlinger in the 60s. I think before I'll try to describe what happened in the cubical case, I'll write the Greendlinger-type theorem so you can see what I'm talking about. So for classical case will be something like this. A minimal reduced. I'm not going to define what it is. Some sort of minimality. So a minimal reduced C6 disk diagram is either a single cell or trivial, or a ladder, which is just a row of two cells, or it has exposed shells or sparse. And those are exactly the positive curvature features that we know now that we have them on the boundary, and we can peel them again and again and do things in induction, shorten words if it's more metric, but a lot of very strong arguments. So this is history. And now I want to discuss what happened for cubical case. So for cubical case, the situation is like this. We know that C prime 1 over 12 is enough to get Greendlinger theorem and a lot of other more strong and beautiful things. And this is, I'm not spelling it right, sorry. Yeah. Round and wide from 2002. And
They define all these notions?
they
define all these notions?
they defined the notion of cubical a small cancellation, and they proved that C prime 1 over 12 is enough for Greendlinger theorem and also for wall space structure, for cubulation in some sense. Also, if you take C prime 1 over 14 hyperbolicity. So, and after it, in 2017, Jankiewicz, I'm not sure I did it correctly, I hope so. She proved that also C9 is enough. Okay, on the other hand, we know that C6 cannot be enough. The way I think about it, like intuitively, is that for the classical case, we need at least hexagon, like in the pairwise sense, in the piecewise sense. So, and then we know that we can get positive curvature on the boundary. But here we have also squares, not just relators. So the squares are flat and they like absorb part of the curvature. So C6 is not enough. So we can ask, what about C7? C7 is also not enough. There's an example, actually not very difficult. Let's see if they have time for it. Yeah, I have a few minutes. So I try to start drawing it. It's not like, I didn't finish it, but you take a square and then you take, those are 7 agons. And then you take again squares and then again 7 agons. I'll try to complete it now. Yeah. And I even have enough place. Well, let's try. Okay, and now again, squares. Here. And here. And here. And here. And here. And now, I'll try to do it with another color.
Closes off. It closes off.
Yeah, you can take, I'll show you in a minute. Okay, I don't really have enough place, but you can imagine it. Now, if you close it like this, so those are 7 agons all the way around. And it's a disk diagram, which satisfy C7 because of the 7 agons. But no, so okay, this is a cubical situation, so it's not exactly shells and sparse or something else, but no exposed cells. Like if you look at something like this, it looks like the same all the way around. So this one, you have pieces like here, but you don't have a lot of pieces on the boundary. It's not like that you have most of it outside. So it's an example.
Counterexample.
Yeah.
So
Sure.
C7 won't do the job.
Yeah.
If you come to example to a particular greedy algorithm, right? Do you know that there are groups like that for which the word problem is undecidable? Just as C7.
It's not exactly the word problem because we are in the cubical situation. So
For the analogous decision problem.
Yeah. So we know that for C7 we don't have like something like Greendlinger theorem, but maybe there's an obvious. Like,
there may be another algorithm,
Yeah.
another decision.
Yeah. Yeah.
Sorry, so in what way are the 7 gons like cubic? They're not squares, they're not...
Yeah, so they come from the relators, okay? Like they are the part that you glue a cone on and then you kill it.
Okay, so what is the cube complex that it starts with?
The cube complex was just a cube complex, and then I took local isometries. Like I took let's say for simplicity, let's take a sub cube complex on it and just kill them. So those are them.
7 ones are folded, right? Like they're not filled in X.
So it's a disk diagram, so you just see the planar part.
They're filled with a cone, not with like...
No, it's a cone. The goal is just to kill all the loops in the cube complex. Okay, so this is what we know about C7, and so now the question is if C8 is enough, and I don't know the answer. I have a very good reason to believe that it's not enough. Also, maybe it's enough like in low dimensions, and I'm not very happy about it because, like, believe me, there are like very good stuff that we can say about the groups if we can find something weaker than C9. So what I'm trying to do now is to find something like a sharp condition somewhere between C8 and C9. But I think this is a story for next time. So thank you for listening.